Happy Friday. This is a lecture on molecular orbital theory to kind of round out the prep for the last homework set that we have here in this Chemistry 1411 class. And that's going to be due the week after Thanksgiving, so we're pretty far ahead. But I wanted you to have some content while I was out of town. And so this is what we've got. So let's jump in. So as far as molecular orbital theory, it is quite a different theory than we have for local bond theory or VSEPR theory. Okay, and why is it a theory? Well, these are theories about the structure of the electron cloud. Now, for hybridization and VSEPR theory, it was pretty easy. We drew the Lewis dot structure. We put all kinds of electron pairs around a central atom, and then we use valence shell electron pair repulsion theory to kind of push those orbitals as far away as possible and to give us the angles of maximum distance between all the electron groups. But molecular orbital theory is going to come in and it's going to change that quite a bit. The local bond theory means that there's two electrons between each pair of atoms that's holding them together. Molecular orbital theory is completely different than that. Molecular orbital theory says that the atomic orbitals come together and they resonate with each other and they allow the electrons to go over the whole molecule. That's where the molecule word comes into play for molecular orbital theory. So let's jump in and see what I'm talking about. So for hybridization, let's go back and review that a little bit, and let's build a molecule with the local bond theory and hybridization. So to make ethene, this molecule here, we've got a bunch of single bonds and some double bonds, and so we're going to bring this molecule together, and each of those carbons are sp2 hybridization, and they're going to form sigma bonds with the hydrogens and with each other. The two carbons are going to have some sigma bonding between the sp2 hybrids. But notice when we make an sp2 hybrid, there's still an unused p orbital. And that unused p orbital can interact side by side and form what we call a pi bond. And so that's what's shown over here on the right. As you can see this interaction here, it says 1 pi bond. So this pi bond is coming from the side-on interaction of that unused p orbital up here. Okay, so what about this idea of this pi bond? If you look at it, it's allowing those electrons to spread over most of the whole molecule. And so that pi bond is really more like a molecular orbital than a local bond type situation. So local bond theory says there's two electrons between each bonded atom. And also it doesn't model excited states well, really. It can model the pi star bond, but it can't model these sigma interactions when they're excited. And so let's look at a new theory in terms of the electron cloud around a molecule, and that is molecular orbital theory. So it allows the electrons to have the largest space to move, because that's what they have in nature. They can move over the whole molecule. As long as there's positive nuclei around, those electrons can be attracted to all of those positive nuclei in the whole molecule. So this is how it works. If we bring two atoms, let's say two hydrogen atoms together, you've got these s orbitals, and as they get closer and closer, they start to interact with each other. Now these spheres are not hard electron clouds. They're always oscillating. And if they're oscillating together, we call them in phase, and they form a bonding orbital. If they're oscillating out of phase, you see this one expands, like it's expanding forward while this one's contracting, and they never ever really interact. And so that's what we would call an anti-bonding orbital. There's a zone in between where they don't touch. In fact, they never really touch. So when they're out of phase like this, we call that an anti-bonding arrangement. When they're in phase like this, they touch each other and they interact, and that's a bonding arrangement. So that the two electrons in that orbital have the whole molecule to move around in. The top one, they still have the whole molecule to move around in, but they have a lot of kinetic energy. And so the kinetic energy is what we're plotting here. And so when something has this break in the middle, we call that a node. and that indicates it has a higher kinetic energy. So if something has more nodes, it's got a higher energy. Okay, so we could bring the p orbitals together and we could form some bonds that way. And the p orbitals can interact end on, and again, if they come in and they're in phase, they're meshing together, we call that a sigma interaction, and we call it a bonding orbital. But if they're out of phase, where they don't really interact, then we would call that a sigma star. It's sigma because the interaction is along the axis of the bond. It's not above and below like a pi, and we'll see pi next. Okay, let's look at the pi interaction. So when those orbitals come together side by side, okay, they can interact like this, where one's expanding but the other's contracting up and down, and they don't really interact much. But if they're both expanding, they can kind of touch up here, and then sometime later they can touch down there. So you can think of the red areas as expanding and the blue areas as contracting. So these orbitals are sloshing up and down on the top half of this graph, and they're never really interacting. Whereas on the bottom half of this page, they're sloshing up and then they're sloshing down, and the whole time they're interacting with each other. And when they interacting with each other, those electrons have the freedom to go over the whole molecule with no nodes. The one on top has a node, and so it's got a higher kinetic energy. And so that means it's again, it's a higher energy, it's an excited state for this molecule. So these are the two types of interactions. We have sigma interactions and we have pi interactions. Notice how the pi interactions are above and below the axis of the bond. And so this is the axis of the bond here. These two dots are the nuclei. And so that axis of the bond is right here. And this interaction takes place above and below. So there's this planar node here that there's no interaction in that plane. It's above that plane or below that plane. So that's a pi interaction. So there's a lot of ALEKS questions having you recognize these different types of interactions so that you just get comfortable learning about them and being able to recognize them. So remember, the two dots in the sketches indicate the two atoms that are being bonded together. And so when you're looking at this, you should recognize some of the previous pictures. And so here again, this is the pi interaction, and these pictures are similar. Okay, you've got this picture here with interactions above and below the two nuclei, and the same with this one down here. And so for the symbol for this particular molecular orbital is the pi molecular orbital, not a pi star, just a pi. It is a bonding molecular orbital, and it's going to be lower in energy than the two p orbitals that interacted. So you have two p orbitals, they interact and they form a bonding arrangement, so they drop in energy. Let's do a bunch of these so that we get comfortable. Okay, here's two s orbitals that came in and they're out of phase with each other. So one's expanding while the other's contracting, and there's a node in the middle. Okay, so you see it's an antibonding orbital, which is a previous slide here. And so notice the symbol, it's a sigma star. So we would label this particular type of orbital sigma star. It is an antibonding orbital because that node breaks the bond. And this is going to be higher in energy than the two s orbitals that came together. So when these s orbitals come together, they're going to be in phase and out of phase, and this molecular orbital is going to be higher in energy than the two s orbitals themselves. Okay, this one here we should recognize from the previous slides. This is a pi star. So this is the p orbitals coming together and interacting, and they're forming this electron cloud shape. And that's a pi star, an antibonding interaction of the p orbitals as they come in side to side. And it's going to be higher than those p orbitals were on each of the atoms. Okay, what about this one? Well, this is the two s orbitals coming in and meshing together, forming a bonding arrangement. And so this is going to be sigma. It's going to be bonding, and it's going to be lower in energy than the two s orbitals that came together from the atoms. So on the atoms, they have this energy, but when they come together and bond, they drop in energy because the electron has a bigger box to play around in and no nodes. Okay, this is the strange shape that you get when the p orbitals come in end on, when they interact end-on and mesh, they form a sigma interaction, which is a bonding interaction, which is lower in energy than the p orbitals on each individual atom. Now, how do we know this actually takes place? Well, one of the experiments is magnetism, paramagnetism. We can put these molecules in a magnetic field and see if they want to, like if the magnetic field pulls them into the magnetic field. That's a measurement of paramagnetism. And anytime the molecule has unpaired electrons in it, then it makes the electron cloud magnetic. If everything's paired up, then we have a diamagnetic molecule. So paramagnetism gives evidence that MO theory is a more accurate view of the electron cloud. We can also really probe the electron cloud using X-ray and ultraviolet photoelectron spectroscopy. For more information on that, just stay with the chemistry degree, and I'll see you in PChem, and I'll explain X-ray and UV photoelectron spectroscopy. It's a great tool. Okay, so here's molecular orbital theory. We have the two s orbitals coming together, and when they're in phase, they form the sigma, and when they're out of phase, they form the sigma star. And then we bring the electrons that came in with those atoms, and we aufbau them up. We build them up from the bottom. And so those first two electrons go into the first molecular orbital down at the bottom. So they're in the sigma molecular orbital, and the sigma star is empty. And we can calculate for diatomics this thing called bond order. So it's the number of bonding electrons minus the number of antibonding electrons. And so we end up with 2 bonding electrons minus 0 antibonding electrons divided by 2, because it takes 2 to make a bond. And so this gives us a bond order of 1, which is accurate. We would model an H2 molecule as having a single bond between them. Notice we're not making bonds by the octet rule in molecular orbital theory. So here's the O2 molecular orbital diagram. Each oxygen atom comes in with 6 valence electrons. We form the sigma and sigma star for the s orbitals, so the s orbitals interacting with each other or being out of phase with each other. Then we have the pz orbitals that are coming in, either in phase with each other interacting, which forms a sigma, or out of phase, way at the top, out of phase with each other, making a sigma star. And then we have the p orbitals coming in, interacting with each other or out of phase with each other, making the pi and the pi star. Now, why are there 2 energy levels next to each other? Well, because you have the px orbitals and the py orbitals. So the pz orbitals are the ones that come in and hit end on. Then the px orbitals and the py orbitals, there's 2 of each, and so we have 2 energy levels, 2 molecular orbitals that can form that way. So then we take the 12 electrons that we have for oxygen and fill them up from the bottom. So the sigma 2s gets 2 electrons, the sigma star gets 2 electrons, the sigma 2px, they have it labeled as x, it's really z, gets 2 electrons, the pi, x and y get 2 electrons, and then the pi stars, we have 2 electrons left. We've used up 10 so far. We put them in the pi star. Now, Hund's rule says we fill them, every electron wants its own orbital first. I mean, it's just like a situation where you come into a crowded room and you want to sit at your own table, right? You want to have your own place. And so an electron comes in, they want their own orbital first, so they go in, spin up, and then we start pairing them up. Okay. So in ALEKS, you get to draw these diagrams. So this is one of the ALEKS problems. You're supposed to draw neon. Now, we don't use the 1s orbitals. The 1s orbitals are held tightly close to the nucleus. They don't interact. They're so tightly bound that when the valence electrons start bumping into it, the 1s's are still close to the nucleus. They're not interacting with each other. It's the 2s orbitals that are interacting and the 2p orbitals that are interacting, because they're bigger, they're further from the nucleus. So for group 2 atoms, you do not draw the 1s orbitals. For group 3, like chlorine, you do not draw the 1s, the 2s, the 2p. You just draw the 3s and the 3p orbitals interacting. Okay, I don't know if they're going to give you any group 3 ones, but if they do, then this would be the sigma 3s, the sigma 3s star, the sigma 3p, etc. So this is for neon, and then you fill it with electrons. Well, neon comes in with 10 electrons each, so that's 20. put them all in there. Once you fill up 20, then you've got all the stars and all the regular orbitals filled, and this would have a bond order of 0, and that's why neon doesn't form an Ne2. Okay, it's just not a stable molecule. So let's look at these molecular orbital diagrams. There's some funny business that goes on, which we learned experimentally, that lithium through nitrogen, because they're so small, they have this thing called sp mixing, and the sigma and the pi here are switched compared to the rest of the periodic table. So oxygen in larger atoms, it goes sigma, sigma star, sigma pi, pi star, sigma star. So it's this pattern here on the right. Okay, but then the lithium through nitrogen, notice these two in the middle are switched. And it's important to get that right so that you can get the questions about paramagnetism correct. In fact, that's how we know this, because of the experiments on paramagnetism. So for C2, we're in this diagram on the left, and we have 4 valence electrons in each carbon. So when they combine, we have 8. So we start filling them up. 2, 4, 6, 7. Let's see. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. You see how that filled in? 5, 6, and that would be paramagnetic if we stop there, but we've got 2 more to go, and so they pair up, and we're at 8, and so we're done. And so this is going to be diamagnetic. Everything's paired up. And the bond order is 6 bonding electrons. So you add up all the ones that are not starred and subtract the ones that are starred. So the ones that are not starred make the bond stronger, and the ones that are starred make the bond weaker because they're anti-bonding. So we take that difference, divide by 2, because it takes 2 electrons to make a bond, and in this case we have a bond order of 2. So the C2 molecule would have a double bond and a couple of lone pairs, 2 on each atom. Now, is this molecule stable? Yes, it has a bond order that's greater than 0, so yes, it's a stable molecule. Okay, let's do O2. All right, for oxygen, we're going to be over on the right. And oxygen, each of those has 6 valence electrons, so they come in and they make 12 together, and so we got to fill it up. 2, 4, 6, 7, 8, 9, 10, 11, 12. Okay, so our electrons are unpaired. So oxygen molecule is paramagnetic, and we know that from experiment too. If we pour liquid oxygen in between the poles of a magnet, it gets stuck. Let's add up the non-starred ones. 2, 4, 6, 8 non-starred ones and 4 starred ones. And so we end up with a bond order of 2. And again, a bond order of 2, that's a double bond. It's a strong molecule, so it's very stable. Okay, let's do another one. Here's nitrogen. This is the one that has the triple bond. Let's see how nitrogen has a triple bond. So we're in the diagram on the left, lithium through nitrogen. Each nitrogen comes in with 5 valence electrons, and so when we bring those 5 electrons together, we have 10. So 2, 4, 5, 6, 7, 8, 9, 10. Okay. And so for the bond order, it's diamagnetic because everything's paired up. And for the bond order, we have 2, 4, 6, 8. 8 non-starred electrons minus 2 antibonding electrons. So that's 6 divided by 2. So we have a bond order of 3. So nitrogen would have a triple bond. So the local bond theory says it has a triple bond because of the octet rule. This has no octet rule. Molecular orbital theory has no octet rule. That's not even a thing. Okay, but we still get the same answer for nitrogen, which is kind of nice. Okay. And a very stable molecule for nitrogen. Now let's do N2 plus. Okay, so they're still on the left. We got 5 valence electrons for each, so we have 10 total, but we've taken 1 away. So we have 9. So 2, 4, 5, 6, 7, 8, 9. So we got 1 unpaired electron. So it'll be slightly paramagnetic. And an experiment would show us that that's the case. And then we can add up the valence electrons. Add up the bonding electrons. We get 7. Subtract 2, so we get 5. Divided by 2 is 2.5. So we have a 2.5 bond order, which is kind of like 2.5 bonds, okay? And we can see the length of this molecule will get a little bit longer because it's got a slightly weaker bond. We see that in experiment. But it's still a stable molecule. Okay, lastly, let's do helium. It doesn't really matter which one of these diagrams we use because we're just dealing with the lowest two levels. So helium comes in with 4 electrons, 2 on each atom. And we make the sigma, and then we make the sigma star. And so it's diamagnetic because it's got paired electrons. But the bond order is 2 bonding and 2 antibonding. So the bond order is 0. So therefore, this is not a stable molecule. And so that's it. In summary, local bond theory says that each bond has 2 electrons assigned to it. This one is useful for creating the shapes of the molecular structure. So we don't throw local bond theory out just because it doesn't quite give us a good view of the electron cloud. We still use it for the shapes of our molecules because it does very well for that. It's very easy to understand. But if we want to really know about the reactivity of a molecule and the structure of the electron cloud, we need to use molecular orbital theory. So that's why we teach that. It also tells us that the atomic orbitals combine to spread over the whole molecule. And this one has experimental support as an accurate picture of the electronic structure of the molecular electron cloud. So even though hybridization is useful for coming up with the 109.5 degree angle and the 120 degree angle and so on, and it's very easy to understand how we get those angles, it's not accurate. Okay, there really aren't any SP hybrids, but you need to learn them as a concept in terms of how we get those angles for the molecular structure. But molecular orbital theory also gives us those angles. It's just much, much more complex. So we'll stick with the simple theory if we're doing things by hand. But if we're really going to do or try to understand the molecular cloud, molecular electron cloud, we would go to some software like a electronic structure software like Gaussian computational chemistry package. And we do that in PChem. So I look forward to seeing you guys in physical chemistry when you get further down into your degree. So I think you have everything you need to complete the last module in ALEKS. And so this is great. And then again, I'll do a summary when I return on the Monday of Thanksgiving week. Until then, have a great weekend.